Now when things go in a circle, wherever you are on that circle, there is a force going to the center of the circle. That corresponds to the acceleration. This is the net force. It's equal to m times v squared over r, because a for circular motion equals v squared over r. So now I want you to consider the Earth and the Moon. We have observed for well over 2,000 years that the Moon goes around the Earth in essentially a circular path. Not quite exactly circular, but close enough for our arguments right now. It goes around the Earth in a circular path. That requires a force. Where does that force come from? It comes from gravity. Isaac Newton was the first to explain this. Now, I'll remind you that if we're on the surface of the Earth, like we are right here over in Hutchinson, Minnesota, if we're on the surface of the Earth, the force of gravity equals mg. We discussed that at length. That should be a very normal, automatic reaction anytime you're dealing with force of gravity or weight on the surface of the Earth. Is the Moon on the surface of the Earth? No, it's way out here. And if you're looking down from the North Pole, it's going around the Earth in a counterclockwise motion. But it's not on the surface, so that doesn't work. But we have to have this force of gravity coming from somewhere. I'm not going to try and spend a lot of time developing Newton's thought process. I don't think that's really helpful to you. But if you look on your equation page, you will find this equation for the force of gravity. This is called Newton's law of universal gravitation. Newton's law of universal gravitation. Make sure you can find it on your page, so you know where it is. So when it comes time to do problems, you can find it. You don't have to have it memorized. If you're struggling, it's in the second column, almost all the way down to the bottom, right next to the other force of gravity equation that we have. And let's open your notebook to your quantities page and make sure that we have these quantities. So F subscript G, what's that? Force of gravity, also known as the weight. What does up and down lines mean? Why would we do an absolute value? Yeah, to eliminate the concern of direction. A fancy way to say that is the magnitude. We want to consider the size of the force of gravity when we do this. This equation does not tell us the direction. To figure out the direction, you need to do a free body diagram. And I will point out one of the fundamental basic things of physics is that gravitational forces are always attractive. Gravitational forces pull two things together. There are four fundamental forces in physics: gravity, electromagnetism, a strong nuclear force, and the weak nuclear force. We'll do electromagnetism second trimester. Strong and weak nuclear forces we're not going to get to. You don't need to worry about those. Right now we're focusing on the force of gravity. It always attracts. Always, always. So if we imagine this being our Earth, so we're right over here at Hutchinson, Minnesota. So drawing you not to scale over here, you have a force of gravity going that way because you are being attracted to the center of the Earth. It's always an attractive force. And yes, if we're standing on the surface of the Earth, we call that down. When you're out here where the Moon is, now you got a whole different thing of which way's down. If you're out here somewhere between the Earth and the Moon, which way's down? That's no longer an appropriate thought. Everybody following me there? We need to have a different way to describe things. So when we talk about gravitational force, when you're not on the surface of the Earth, we describe it as an attractive force. The two things are attracting each other. It happens everywhere. It happens on the surface of the Earth, and it happens everywhere else. If we're on the surface, we like to use this because it's easier, right? Pretty simple that way. But if we're not on the surface, we need to do this. So again, the absolute value signs mean that we're finding the magnitude of the force, the size, not considering the direction. You got to look back to your free body diagrams to find your direction. Then we have big G. Big G. called the universal gravitational constant. The universal gravitational constant. Turn your equation pages over. Formula sheets over. Universal gravitational constant. We'll get there. Look at, do you have your equation sheet? Oh, you don't have anything on the backside of your equation sheet. Slide over here next to Ms. Renner a little bit closer so you can share with her for now. On the backside, up at the top, there's a box that says tables of constants, etc. One of those we've seen many times before. That's little g. What's little g? Acceleration due to gravity. Fancy people in physics would like you to call it the gravitational field constant. Symbol is little g. The value, the magnitude, notice there's no direction on there, is 9.8 meters per second squared. Right near that, there's the big G. You see where it says universal gravitational constant there? So big G. It's a constant. It's always the same. It's equal to 6.67 times 10 to the minus 11th. What are the units? Meters cubed over kilograms and seconds squared. Now, that's not the way I've memorized it. I've memorized the value of the units to be newtons times meter squared over kilogram squared. It turns out to be the same, so I might stumble into that once in a while, just warning you. It works the same. So there's your units that you were just asking about. What are they? What are the units over here? And this big G right there? Yeah. Yeah, there's your units. You might even put the number in front of there when you're doing this, because the number's always the same. 6.67 times 10 to the minus 11th, what? Meters cubed over kilograms and seconds squared. That should be telling you that the label for this G, since it includes kilograms and meters and seconds, these two things have to be in kilograms. What do you think M stands for? Mass. So that was tough. And R is radius. You should have that there already. What does this radius thing mean? Distance from one object to the other. Why is that a radius? It might have uniform circular motion. So right now, Fraser and I are about a meter apart. Why would we describe that as a radius? Because if I shuffle over here, we're still about a meter apart. And if I shuffle over here, we're still about a meter apart. And if I continue doing that, I would have a circle, and that would be the radius of the circle. Does that make sense to everybody? I make extra point about this because one of the common mistakes that people make with this is we say, okay, the distance from this object to this object is whatever we say it is, and people go, oh, I got to divide that by 2 to find the radius. No, that is the radius. That's not the diameter. That's the radius. That's the distance between them. Make sure when you're doing this that it's in meters, and make sure that you square it. I emphasize this because I am seeing, as a very common mistake, when we do this, people forgetting to square the velocity. And from previous experience, I know that very many people forget to square this radius. So let's consider some of the implications for this. Some of the situations that come up. This means, for example, I'm sure Gregor just loves this, because I'm standing here next to him, he's attracted to me. Does he notice that? Why does he not notice any difference in attraction if I'm here or if I'm way back over here?
Because G is a really small number.
That's a really small number, so the force of attraction between us is really small. And a much bigger attraction that he's very much aware of, at least subconsciously, if not consciously, is the attraction for the Earth. So there's a force of attraction between you and the Earth. And when I say between you and the Earth, that means the Earth attracts you, but you also attract the Earth with the exact same amount of force. So it depends, as you do this, on your free body diagram. In other words, if I take back to the moon is being attracted to the Earth, and we can count that as a force of attraction, the force will be going that direction. Everybody with me there? But if the object I'm considering is the Earth is attracted to the moon, and now because the Earth is the focus of my free body diagram, the force of attraction would be going that way. That's why we have absolute value signs here. We have to consider the free body diagram to figure out the direction. Every time. So we've been doing this for like 4 weeks now. Every time we have forces, free body diagram time. Every time we have forces. First step, do a free body diagram. Some of you have gotten lazy on that, and you've been caught. Some of you have gotten lazy on that and haven't been caught so bad yet. But you will. If you haven't figured this out by now, I want to emphasize, this is too much for anybody to do in their head. There are too many relationships here to do this in your head. If you try and do it in your head, you're going to make a mistake, and when you make that mistake, it's going to hurt big time because I can't figure out what you're doing. Show me your work. Don't start getting lazy now. Now some of you go, I'm senior. It's almost second try. I get the coast. If you've ever run track, if you've ever done something across country, if you've ever played in a state championship hockey game, you fight to the very end. I bring this up because a couple of years ago, two young ladies were playing in the state, it was a third place game, it wasn't a championship game, sorry. They quit. Hutch quit with 20 seconds left. They were tired, and they lost with 20 seconds left. You want to lose, coast. You want to win, you sprint to the finish. Your finish is coming up in June. Sprint to the finish. So let's do a sample problem. So here's the question. How fast does the moon go as it orbits the Earth? I am going to purposely do this as much as I can without numbers. Put numbers in at the end. This involves an orbit. What is an orbit? It goes around something. If it goes around something, we're dealing with circular motion. And circular motion deals with forces, and forces need a free body diagram. So your first step is here's the Earth, here's the moon. And again, if we're looking down from the North Pole, or from above the North Pole at the Earth, the moon is going around counterclockwise. I don't care that you know that. That's not such a big deal for physics. If you were taking astronomy, that would be a big deal, because there's a whole bunch of things about that, but that's beyond physics right now. So here's our diagram. We need to put our forces on here. What forces do we have? We have the force of gravity on the moon. We're asking about the moon, so we want to do the free body diagram for the moon. Yes, there's only one force. That should make life a little bit easier, but you still need to do a free body diagram. So the net force is equal to the force of gravity. And because it's going in a circle, what does the net force equal? M, and I put M sub M, because that's the mass of the moon. Because it's the moon that's moving. Is everybody with me so far? But now we have a problem that we couldn't do before, because Fg is not equal to mg, because the moon's not on the surface of the Earth. What's Fg equal to? Big G times the mass of the Earth times the mass of the moon divided by the radius squared. It would be the absolute value, so we don't have to worry about direction. In other words, it doesn't matter if we do it here, or here, or here, or over here. So when I'm doing this, I'm leaving off all the negative signs, if there happens to be any. All right, any other questions? So now, substitute this in. So I have big G times the mass of the moon times the mass of the Earth divided by the radius squared equals the mass of the moon times the velocity squared divided by the radius. Any questions on that? A little bit of algebra. Mass of the moon cancels. One of the radiuses cancel. So big G times the mass of the Earth divided by the radius equals velocity squared. How do we find velocity? Square root of both. Get velocity by itself. So square root of G times the mass of the Earth over the radius gives us the velocity.
What's the big G? Oh,
What is the big G? I was just about to ask that. It's called the universal gravitational constant. What is it? A little louder, Yonder, so all the people way in the back can hear you.
6.67 times 10 to the negative 11 meters cubed per kilogram per second squared.
All right. So we got G. How about mass of the Earth? Homework packets. Page, what page am I on? 1, 2, 3, 4, page 5. Homework packets. Question number 1, it said calculate the mass of the Earth, so you can use that for this problem. That would be another problem for you to test. Can you do that? Can you calculate the mass of the Earth? And then we have a whole bunch of other numbers up there. Which of all those numbers that we have up there is the R for this problem? The distance from the moon to the Earth, which is 3.8 times 10 to the 5th kilometers. Ouch. Why did I say ouch? Not only is it a big number, G has units of meters, and this is in kilometers. So what do you need to do? Change your kilometers to meters. And again, do not get lazy. Show me your work. It is not hard to do, but you need to do it. So we have 3.80 times 10 to the 5th, I think it was, yes? Kilometers. This is a better 5. Times 1,000 meters for 1 kilometer. So that's going to give us 3.80 times 10 to the 8th meters. There's the R. Make sure that you take the time to change the units before you stick them in here. Especially if you're doing R squared, because if you try and do it afterwards, it gets to be really messy. Because there's not 1,000 meters squared in a kilometer squared. There's 1,000,000 meters squared in a kilometer squared. And most of you would have no clue where that comes from and get really lost. So do it first. Make it easy. Questions on this one? I'm not going to put the numbers in. You should be able to do that. And by the way, once you have that velocity, you should be able to figure out how long it takes for the moon to go around the Earth in days. And see what it takes to go from a full moon to another full moon. What is it? Does anybody know? We got a full moon tomorrow. How long do we got to wait for the next one? A month. 4 weeks, plus a little bit extra. So if you wanted to check that, throw that out there.
How do we know the mass of the Earth?
It was in answer for number 1. Let's do that. How do we know the mass of the Earth? Did we go and get a really big balance and put the Earth on the balance to measure the mass? No, that's not what we did. We said, okay, here's the Earth. Here's you standing on the Earth. We're dealing with forces, so what am I doing? I'm drawing a free body diagram.
I have a question.
Yep.
Did they weigh the Earth? Did they account for all the things on the Earth that we should know?
They all came from the Earth in the first place.
That's true. You think of that.
So it was already here, we just changed what it looks like. So on you have the force of gravity going down. We also have the force normal going up. And if you want to consider the Earth, if we did that just for fun, here's the Earth, here's you. Looking at the Earth's free body diagram, we have the force of gravity going that way between you and the Earth, so you're pulling the Earth up. And there's a surface here, so there's a force normal going that way. Just pointing out it happens both ways. I'm not going to spend a lot of time on that. This is you and the Earth. That's you and the Earth. But here we're drawing the free body diagram for the Earth. Here we do it for you. Okay? So considering that free body diagram, I'm going to start with this. Some people are going, why would you do that? Why would you say the force of gravity equals the force of gravity? Because the force of gravity is equal to the mass of u times acceleration of gravity. Force of gravity equals mg. We've done that for a long, long time. But today we also learned that the force of gravity is g times m1 times m2 over r squared. Everybody with me so far? Your mass cancels. Oh, the Earth's mass does not depend on your mass. Isn't that cool? We're trying to find the mass of the Earth. To do the algebra, how do you get the mass of the Earth by itself?
Times by r squared.
So g times r squared over big G equals the mass of the Earth. Did I lose anybody in that algebra? So we know G, we've done this, we've measured this many times. What's that equal to? 9.8. Yeah, negative, you want to put a direction on there, but I'll go back. These are absolute values, so we're not worrying about direction on here, so we'll leave the negative off. Times R, what's the radius of the Earth? 6,370 what? Kilometers. How do we know that? Yeah.
25.
There was a guy about 300, 400 BC that measured the radius of the Earth. Long before Columbus ever sailed the oceans blue and everybody was afraid he was going to fall off the end. We have lots of people, Greek mathematicians for the most part, that had done multiple measurements to figure out the circumference and the radius of the Earth. That's been done for a long time. I don't expect you to memorize it. Whoops, got my 6. Radius is 6,370 kilometers. Plus or minus a few kilometers because of the mountains and the valleys and all the rest of that. So let's put it in.